This session will look at the naive Bayes classification. So as with logistic regression, we're going to be looking at a form of supervised classification. And again, we'll be looking at probabilities as we did with logistic regression. This, the Bayesian theory behind this, which is basically conditional probabilities, this is really old. This goes back to Thomas Bayes, who was a monk, and he came up with this theorem of conditional probabilities all the way back in 1763. So the principles behind using a naive Bayes classifier is a really old idea. These machine learning techniques in general, they are quite old, most of them, and until you get into deep learning. So we're going to look at a very old technique, and it involves conditional probabilities. And so Thomas Bayes, or Bayes' theorem, sets out this equation. So we have some outcome A. We want to know the probability of A given some evidence B. And Bayesian theory states that this equals to the probability of observing B given the outcome A that you're interested in. And this might seem a bit confusing, but we'll break it down with a few examples. Multiplied by the probability of seeing A in the population, divided by all evidence in the population. So this would be the evidence for B and A. So we see that, breaking it down, if you want to know the probability of A given some evidence, well, you should know in advance what the probability of observing the event is, regardless of any evidence. So this could be the number of people in the population that have epilepsy. The probability of B, so this might be the probability of people that experience seizures. So you can see where this first term comes from in the numerator. This is, what is the likelihood I will see seizures in people that have epilepsy, multiplied by the number of people that have epilepsy in the population. So these are all things that we can find out in advance. And what we would like to do is say, well, what's the probability that this person in front of me has epilepsy if they are experiencing seizures? And just to hammer this home again, so to rephrase this, in terms of the probability of dementia in the population, which we know, you can go and find this up, you can look it up, it's about 6% in over 60s. And one assessment of dementia is something called a mini mental state exam score, which is basically a test for cognition. And depending on how you score, that you will be assessed as a candidate for having dementia. And so P of A, which is what we are really interested in this case, is what is the probability someone has dementia given their mini mental state exam score? And to reverse this, what is the probability of B given A? Well, this is, what is the probability that someone will achieve a certain score given that they have dementia? And then lastly, you can view this probability of B as seeing the probability that people have dementia given their mini mental state exam score, plus the probability of not having dementia given their mini mental state exam score. So this is the evidence of both. And as you can imagine, this P of B, the denominator, this is fixed. So no matter what calculation you do, if you want to look at the probability of not having dementia given some evidence, instead of the probability of having dementia given some evidence, P of B, the denominator, always stays the same because it has both components of the equation. Okay, and also, as in with multiple linear regression, multiple logistic regression, we don't just have to have one feature that we use to predict on, we can have multiple features, and also multiple classes. So this is an advantage of naive Bayes over logistic regression. If you remember, logistic regression could only classify with binary variables. So here we denote C of K, where K can equal 1, 2, 3, upwards of different classes. And we can also have multiple features. So we can rephrase this Bayes theorem in terms of number of features and number of classes. So let's think of a theoretical question, and we'll try and answer this using naive Bayes, the principles behind it. So if a patient reports to the hospital with symptoms, the doctor diagnoses the patient based on these symptoms. Can we use naive Bayes or Bayesian theory to classify new patients based on their reported symptoms? So this is telling us we're going to gather some evidence first. We're going to observe various symptoms in the population and what diagnoses they have. And we're going to use that knowledge we gain collecting our real world evidence. When a new patient comes in, they tell us their symptoms, and we have to use naive Bayes to classify based on our training data. So this is what our real world data might look like. We know these things in advance. Okay, so these person that, you know, there'll be some technique or diagnosis where you can say this person definitely has cold. So this is our ground truth, real world evidence data. And we can work a few things out from this. So for example, if I asked you what the probability of flu was, or P of A in the numerator, it's simply the number of people that have flu in the population, which is 4/7. And the number of people that have cold, P of cold, is just 3/7, which is 3 people. Strep throat, probability of observing strep throat in the population is just the number of people that have strep throat. And where it gets a little bit interesting is, what's the probability of observing strep throat given that the person has cold? And there were 3 people that have a cold, and the first one has strep throat, the second one has strep throat, and the third one does. So the probability here is 1. So these things are actually really easy to work out. The Bayes theorem equation might look a bit confusing at first, but actually the individual components, they're super easy to calculate. They're just frequencies. And, you know, frequency here is probability. So we can say, well, the probability of flu, given our features, which are strep throat, cold, strep throat, migraine, temperature, things like this. You just take the probability of strep throat given flu, multiplied by the probability of migraine given flu, blah, 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 multiplied by the probability of flu. And then in the denominator, it's just P of B. So you'll notice again that P of B is just normalized to include both cases, flu and cold. The numerator here is just the first half of the denominator. You see, so flu multiplied by strep throat given flu, and so on. So you take the numerator, and that's the first component of P of B, and then you just take the opposite for cold, and that is the second component of our denominator. And what you do is you calculate this equation twice, the first time for flu, the first time for cold, and you simply take the larger probability. And this is sometimes called the maximum posterior. Whichever comes out the largest is your probability. Is your class you should say they are. And these aren't mutually exclusive. So it wouldn't be that flu would be, if flu was 0.6, then cold has to be 0.4. That's not how it works. These aren't exclusive with each other. You could have that the probability of flu is 90%, but the probability of cold is 91%, in which case you would say this person has cold. Okay, so it's pretty simple things to work out. So there was a concept here of training. So we did talk briefly about this in logistic regression. Again, naive Bayes just relies on the real world data to learn these maximum posteriors. It learns entities like this. And then once it's done that, then you can take in an unseen sample and test if they have flu or cold based on their symptoms. So that's what we're talking about here. After we've trained, used some training data, we've learned the parameters, things like what's the probability of strep throat given that they have cold. Once you've learned those, then you can take a test set. And then, as I said, just take the max of the probabilities. But that was with categorical data or binary data. Do they have strep throat, yes or no? So what about continuous features? We looked at the normal distribution yesterday when we gave an example of maximum likelihood estimation when we were looking at the logistic regression equation. And actually, this is the equation for a normal distribution or a Gaussian distribution. And what we can do is when we take our training data, we can estimate things like for people that have cold, what's the average, I don't know, blood pressure of people that have a cold? Or what's the average temperature of people that have a cold? So we can work that out from our training data. And we can also work out the standard deviation as well. So if the average is here or the mean is here, we might say that this green curve represents people with cold and their average temperature is lower than people in this blue curve that have flu. So again, we can observe these things from our training data. And all we need to do is to plug these values. So we have the mean here of temperature for people that have cold. We just put these into the equations, and again, standard deviation. So let's have a look at this in practice. We have a continuous variable, and just to make this a bit more difficult, we'll have a second continuous variable. And when you combine these two together, you have these two means where they intersect. You create your standard deviations. When you plot these two features against each other, you can either have 2 standard deviations or 3 standard deviations from the mean. And what we'll do is we'll add in a second class. So this might be people that have flu in red. This may be people that have cold. And we're plotting temperature against some other continuous variable, which I can't think of a good example right now. But anyway, both of these classes, they will have distributions which look a bit like this when you plot 2 continuous variables against each other. And what we would like to do is to take a new data point. Once we've trained these, we've learned the mean. We learned the mean of each group and the standard deviations doing training. We'd like to take a test sample, put it anywhere on this plot, and decide which distribution it belongs to out of the 2. So we're going to say, given a height X and a weight Y, what is the probability that the person belongs to a certain class, maybe adults or children? And we're going to have access to the mean and the standard deviation of those classes, because that's what we collect in our training data. So how do we do this with naive Bayes? I mean, this is our original equation, and we need to change this somehow. But just look at the principles. We have the probability of adult given, and then we have the probability of B observing some value in a continuous variable, given that they're an adult. So contained within here is a distribution. It's not a frequency anymore. It's a distribution here. So we need to sub in equations for our Gaussian distribution into these variables. So let's just work this through. The easiest one is probability of A. Well, how many adults are there in the population? This remains a frequency calculation. And we might say, I just pulled this figure out of my head, doesn't mean anything really. The probability of observing an adult in a sample population is 40%, because 40% of the population are adults. Now, probability of getting a value of weight given that it's an adult. So how can we work this out? We take our equation, our Gaussian distribution. Remember, during training, we learned what the standard deviation and the mean was for adults in terms of weight. And now we just need to sub in a value for X. So if you give me, 68 kilograms, I'm going to plug that number into our distribution that we've learned, where the standard deviation and the mean are given that they are adults. Okay, I'm just going to plug this in, and I would also do the same with children as well, because we're calculating the argmax of these two. Let's just see how this works. We take our PB, given a value of weight, and that we have an adult. What's the probability that I observe this weight? And so we just plug it in. It becomes this. So what's the probability that we have a weight of an adult given the mean and standard deviation of adults? We just plug our values in. So it might look a bit like this. We have some value of maybe weight or temperature or whatever it is, and we also have some value of height, denoted by this point here. Now, clearly, we can see that it lies within the red distribution, but we still need to make the calculation anyway. What we observe is that when you take the raw value, you can compare it to how far it is away from the mean of each class. So we can see clearly it's closer to the red class here, but maybe in the other variable, it's slightly closer to the black class here. We just plug these in. So, given weight or height, we can just plug in the various values and out pops our probability. So that's how you would include continuous variables in your calculation for a naive Bayes classifier. And the big picture is it becomes this. So the probability of adult, which stays as normal, but then we have to sub in our So this is all one term here, so that P of B, given some evidence, is this, or the probability I observe a certain weight, given that I have an adult sitting in front of me, is this, and so on. So that's P of, what's the probability that this is an adult, given their weight and height and so on. And you can see how they map to the original equations. You would do this for probability of children too, as well, and just take the larger probability. Easy. So in summary, for naive Bayes classifier, it outputs probabilities for each class given some evidence, and the probabilities are conditional given the evidence. If we compute the probabilities of two classes, we can classify the instance as one class or the other by simply looking at which has the highest probability. And we can choose an appropriate probability threshold depending on the problem, i.e., we can accept a lower probability for a certain class if we need to pick up as many classes as possible. We'll look into this problem a bit more, and we do hyperparameter tuning and ROC analysis on Wednesday morning. Okay, so let's dive into the notebook. And the data that we're using today is just a very small genetic mutation data set, and we'll explore it quickly here. Basically, we have some variables, and the output is either that the mutation is benign or is pathogenic, i.e. disease causing. So it's just a binary classification. Remember, naive Bayes can handle more than just two labels. It can do multi-class labeling. And so we read our data in. That's the first thing. And we're going to use the E1071 library, which contains a few different machine learning algorithms. It contains naive Bayes. This was created by, I can't remember, the University of Colorado, some students there. They happen to share this room, E1071. So that's where it gets its name from. So we read in our data, and we can get simple summaries. And if we scroll all the way down, we can see our labels here. So there are more benign mutations than there are disease causing, which reflects life. Only 0.001% of mutations generally do contribute to disease. And what we're going to do is split our data into training and test set. So we're going to determine first how many rows of data there are. And there's 10,000. So what we do is we are going to get 75% of those rows. And we're going to store that in an object called bound. And what we're going to say is first shuffle our data. So sample command shuffles your data. Usually you can use it to pick one random row. So you could do something like this. Okay, that's one random row. But all we say to just completely shuffle our data, instead of choosing one random row, we'll set this to the number of rows in the data set, 10,000. So just completely reshuffles the data. And then we're going to split this into a training and test set. So the rows from 1 up to 75% of the rows of the table becomes our training data. And then the remaining rows become our test set. So that's the first thing we do. And let me just check why I've got that error. There you go, it's fine. So we do that, and then the call to naive Bayes, again, this comes from the E1071 package, it's just naive Bayes. And we know this formula now, we're getting used to it. Our labels was our target column, and I'm going to put in all variables because I'm lazy. So we put in all variables with the dot notation and so on. So let's see how it runs. It's very quick, and let's just check the output. So can I bring the cursor down? There we go. So the first thing is it's learned from our training data what the probabilities are, the probabilities that it should be learning. So it knows, for example, that there's roughly 2/3 of benign mutations in the data set. So the probability of observing, P of A, of observing benign is about 66%. And then we got our conditional probabilities. So given some score, or given one variable. And we want to ask, what's the probability of observing a certain value of a variable, given that they're benign or pathogenic? So we have all these conditional probabilities as well. These are our P of A given B. And it computes all of these for us. So that's the output. We've trained a classifier. We've estimated our prior probabilities. Now we just use the predict function. So we've saved our model, our trained model into this. We just put in our test set and save that into an object called nb.pd. And we can compute a contingency table, i.e. a confusion matrix, by plotting the predicted values against the ground truth. So just to show you what they look like, again, so we're predicting that an instance is either benign or pathogenic, and then we also have our ground truth. So we want to compare these pairwise, these two matrices. And that's what you end up with, is your nice confusion matrix. Oh, sorry. Which is good. Now, so in machine learning, or any data analysis really, you'll often come up with a sample of data where you have some missing data in there. And so I'm going to show you a nice package to help you deal with missing data. First, just why do we get missing data in the first place? Sometimes you'll have data where it's missing at random, which in that case, you might be okay to do something like just take the average. Where you see a missing value, just take the average of the column. That might be one way of dealing with missing data. If you have data which isn't missing at random, so maybe there were 2 or 3 people responsible for data collection, and the third person who was collecting their data, they misinterpreted the brief and they didn't fill in some data properly, so it's incorrect, i.e. you may as well just class that as missing data, or they just forgot to fill in a column. If you've got systematic missing data like that, then I think you're a bit stuck really. You might just have to discard that column of data because it's not missing at random. We can't really deal with it if it's missing for a certain reason. We can't estimate why that would have been. So anyway, I'm going to take you through the mice package, and really I would only recommend trying to augment your data or impute your data when you have missing values, when the missing values are there for a random reason. Yeah, so we have this mice package, and it escapes me what it stands for. Is a multiple imputation something or other. Basically, what it's going to do is, instead of just doing quite a crude thing where you take the average of the column to replace the missing data, it's going to use just some form of regression to get all the variables in your data set and predict a value on the continuous column. So we know in regression we can predict a value of continuous data. So a lot of these imputation techniques to deal with missing data, that's what they do. They do some form of regression. There are loads of different variations on that theme, and mice is a package which does this quite nicely. So the first thing to do, we're going to simulate some missing data. We'll take our original data set, Humvar, and we're going to use this ampute function from mice to synthetically generate 10% missing data within our data set. And what we can do, again, any object. So, you can look inside an object to see what's there by putting ls around it. So if you're familiar with Linux, you'll know what this means. So these are all the objects within this df.missing. We use this function here. So we can look inside any of these objects, and we can look inside, for start, the amp object. So we use a $amp to access it and see what that is. So this is our new data with missing values. And to ensure that we do have missing values, we'll just take a summary. And as you can see here in each column, there are some missing values within those columns. So now we've got some missing data. How do we use the mice package to fix this issue? So yes, we'll talk about the how you do data imputation. The first thing to consider, though, is if you look at all the columns of data that we have, we have some missing data in our labels column. So we don't want to do this. If you don't have the value for your labels column, then they're useless to you because you don't know what they are. There is an argument to say that you can randomly have some missing data in your label, and your classifier should have difficulty arriving at a probability either way on benign or pathogenic. So you can do that as a third test if you like, but I would just remove them if you don't have it. So we don't want this to happen. We're going to preserve our labels. So we're going to take the labels from the original data set, just put them into an object called df2 to keep them aside. We'll rejoin them later with our data. And we do use the mice function to impute our data. And then you can see the complete version of the data set using this function called complete. So this comes on the mice package as well. So we have our complete data here, as you can see. You can do a summary command on this. And there you go. So there's no NAs anymore. Actually, there is in there. Why is there one in this column? I'll have to look into that. Probably because it couldn't converge on a value. So yeah, you can see that it's not perfect. Anyway, let's take our newly imputed data set. We'll turn it into a test set and train set as we do before. And we'll just run naive Bayes on our repaired data set. So there you go. So we can train a model, and then we can test our model. So we use the predict function, and we can produce our confusion matrix. So, even if you're faced with missing data, there are certain ways to handle this. The mice package is just one. There are loads of packages, and I encourage you to explore different ones for certain situations. Yes, so one thing to take into account when you're making predictions, the training data, you are effectively using fake data, it's synthetic data to some point. So, I think when you do regression to fill in the missing values, it's trying to find the best value to fit the distribution. But in the real world data, things might not be that simple. You could have some values in there which buck the trend of the distribution that you're trying to fit. And so when you impute the data using some form of regression, you tend to miss out on those nuanced examples where they don't really fit the original distribution. So I think what you find in general is that when you train using imputed data, you tend to inflate your accuracy somewhat because of that reason. You're making the data more perfect, if you like, to fit a distribution, when in reality that's not always the case. Anyway, so yeah, we can look at not only the classes that you predict, whether it's benign or pathogenic. We can add this parameter here to the predict function type equals raw, and it will give us the raw probabilities. So this is the probability that a certain sample is benign, and in this case, they're very sure that they're benign because it's 0.999 whatever %. And we can plot those probabilities in a histogram, and we can see that there's this huge gulf in between. So this should be the data lends itself well to classification, because we can see that most of one class is on one side of our probability distribution, and most of them are on another, with not much in between. So really, we could choose a probability threshold. We don't have to just stick with 0.5 as we looked at in logistic regression. We could pretty much choose any threshold within this valley, if you like, and it would do a really good job at classification. So that's what we mean by you can bias the probability at the end to suit your purpose. So just to point out, there are a few different libraries for naive Bayes. There's one called the CLAR package, and instead of creating this horrible clunky graph that I've produced here using the hist command, it can do it for you. So we just run naive Bayes and we plot it, and you can see Kaggle has squashed our screen, which is slightly annoying. And I think it's duplicated some of the plots. But you can basically see, and this is not in a binary classification, there's 3 classes here. You can see how the probabilities do overlap. So this would be difficult to tell because at some point, the blue class looks as if it becomes the red class because this is overlap. So anyway, that's naive Bayes in a nutshell. I think for the lab session, it'd be good to compare how naive Bayes does against logistic regression. Obviously, you can't do it with the iris data set on logistic regression, but you could definitely use the HumVar data set. So I hope you enjoyed this notebook, and you can see how we can run naive Bayes in a supervised classification setting.